Hello everyone, it's Sean and welcome back to Having Fun Repairs. Now, in the previous video that just released, we did this revival of our Philco 38-4, okay? Now, one of the things I had to do towards the end of repairing that radio was select a new audio output transformer. And I didn't really get into too much how I went about my selection because the video was it was way too long as it is. It's an hour and 20 minutes approximately. And I just didn't feel like that was conducive to explore all that inside the context of that video and the intent of that video itself. And so I wanted to come back to this as a separate video and just kind of go over how and why I chose this 125E kind of universal audio output transformer in lieu of getting an exact like of the transformer that was inside the radio. Now, there's a few things that I considered going into selecting an output transformer. One of those things being, I'll get this kind of set out of the way for a second. Power considerations. So P, power, and we'll say either P or W or watts. Okay. I'm also concerned with DC as direct current resistance, usually expressed in ohms, the big omega symbol. Also concerned with AC impedance, which is also expressed in ohms, but it's this weird little W symbol, okay? Those are my primary considerations that I went into with selecting a alternative to what we originally had in here. Now, when you deal with transformers for a while, this Philco one that was pulled out was a 32-7754, and then it's stamped the letter M right on the end of it. Okay, I couldn't find a like for like online. One of the individuals I spoke to on a vintage radio forum did have one, but it had the same issue that this one had, where at one end on a winding, it was showing high resistance versus what it should be showing. Okay. And when we get into the schematic, okay, i.e. this schematic here and what it's showing to us, we can see down in this section, we have a filled coil rated for 660 ohms. That's a known value, okay? And then over here is our output transformer with center tap. And we can see from center tap to one end, we have about 350 ohms. And from center tap to the other end, 310 ohms. So a total of 660 ohms of DC resistance. And how do I know that that's DC resistance? Well, it would be verifiable measuring a DC resistance with a volt ohm meter. Okay. So you're kind of probably asking yourself, well, why do I care about power, DC resistance, and AC impedance? Well, for me, it's all about matching numbers. Okay. Now, when I peruse a lot of vintage radio restoration websites and articles and forums and stuff like that, one of the things that is constantly mentioned is your output transformer is typically used as a choke, not just impedance matching and getting an audio signal um, over onto a electromagnetic speaker, because that's what essentially what this is. It's not a permanent magnet, okay, to produce a sound. And there are some people who would replace, if they couldn't get an exact thing, they would replace with a permanent magnet speaker. They do away with the output transformer, and then they put in a high wattage resistor at the same DC resistance respective of our circuit. Okay, so 660 ohms at probably about whatever power rating we have there. And a lot of people seem to argue with that. I'm not really too much either way. I can see how without this performing isolation, that is an electrical hazard. Potentially a lot of current. So that would give me hesitation, to say the least. So what I opted for instead is, since I couldn't find a like for like that was going to have the same frequency response, the same DC impedance, maybe not the same Henry rating, that I would get a substitute and try to get those numbers as close as possible, so we don't have a significant standing wave ratio or high VisBar. Okay. Now, if it alters the frequency a little bit, your frequency response, yeah, I think that's a sacrifice, given that this is going to perform isolation, and the output is going to be relatively safer. Okay, so how did I go about making the selection? Well, typically I do these kinds of videos over on Patreon, paid for type videos, but I figured I would release this one here simply because there's a lot more people with a lot more knowledge than me, especially in a vintage radio realm. And if any of those people are watching this, given my inexperience, they can come back and comment on this video, explain to me what I should do different, and I will accept that. So I'm not taking what I do here as absolute. I'm simply looking at numbers and doing math and trying to make things match as close as possible. Okay. So I'm not putting this over on Patreon, even though this will be a part of my HFR learning series. I just figured this was a way to teach something, along with getting feedback, especially from the vintage radio, groups of people out there who've done this a lot longer than I have. I'm still learning along the process. Okay, so let's get into power. Power is the first thing that I need to concern myself with. Now, you can kind of guess, depending on how often you've worked with transformers, what the rated power is for. We can see that this one's a tad bit bigger than this one. So if I had to guess, okay, I would assume that this is probably a 10 watt transformer. Now, I went with a 15 watt transformer, just to give me a little bit overhead. But let me show you how I went about calculating power. By the way, some of these things I'm showing in this video, I go into more detail with over on my Patreon concerning DC circuit principles. We've now started on AC circuit principles as well. But here goes a bit of application. Let's do a power consideration. Okay, power consideration. Highly encourage you to get something like what I got here, this document, downloading a RCA receiving tube manual. Okay, because you often find more information inside of these manuals than you do just the data sheet for your vacuum tube itself. And sometimes not, sometimes it's the same information, but this kind of puts everything into one area to kind of look up stuff. Okay, so I'm looking at this full wave vacuum rectifier. That is the 5Y4G that we use inside this radio as our full wave bridge rectifier. And I look at this, DC output voltage to choke, and I annotate that is 390 volts. So I write that down from our 5Y4G DC output to choke, 390 volts. Okay. And now I need to pull up our push-pull audio amplifiers. Okay. And I need to check basically the plate voltage of them to see what our voltage drop is. And those were 6F6G if I'm not mistaken. So let me find it. And yeah, here we go. 6F6G power pentode and push-pull class A amplifier configuration. We have a plate voltage listed here of 315. Okay, 315. Well, if I was to say take that voltage and subtract them, that means we got 75 volts. Okay, now we already have two values that we need in order to determine power. Okay, so P equals V squared over resistance. Okay, and let's see. Yeah. Because I'd rather do math by a calculator, I think that will prove that I'm not doing it incorrectly at a minimum. Let's come up here. 75 times 75, 5,625. We divide that by 660. And we can see that our power is 8.5 watts. So 8.5 watts. Well, that's a little bit lower than the actual, diagram tells us. I think it's listed there as 10.5 watts somewhere. I'd have to find it again, but I think that's what it was listed as. But either way, we can at least see 11 watts. There we go. Maximum signal power output is 11 watts. So that's the max. Okay. But in, respect of this radio and application and those voltages, we're looking at 8.5. So I need to consider an output transformer rated above 8.5. A 10 or a 15 watt transformer is perfectly fine in this regard. Obviously, as I stated, I went with a 15 watt transformer. Okay. Now, when I went with that 15 watt transformer, pull out my multimeter here, and we'll put it on a DC resistance measurement. And what I'm going to do is measure DC resistance from center tap to winding in and center tap to the other end of the other winding. Okay, or the same winding, sorry. This is on our primary side. So we've got 75.6 on one side. So this is our primary winding. Here goes the center tap, 75.6. And then if I measured on the other side, we got 82.5. 82.3. 82.3. 82.3. Well, that's a far cry, even if I total that up from these numbers here, okay, and our entire DC resistance of 660 ohms, which we need to match with our fill coil, which is also rated DC resistance rating of 660 ohms. As a matter of fact, if I go across the fill coil, you can see it right there, 660 ohms, or 0.660 k ohms as my multimeter is showing. But there you go. That's a far cry. So what I did is I just said, okay, they're about even. I said 80 one side, 80 the other side. Well, 80 minus let's say if they were going to be about 320 each side, 80 minus 3 or 320 minus 80 is like 250 or whatever. Excuse me. Even both sides would be, 320 each side, not, or 330, not 320, and that would give us a 660. I don't know what I was thinking. But anyways, if we said 80 was even from the center tap, then yeah, we're looking at needing an additional 250 ohms of resistance from center tap to each end of the winding. So what I did was I got two 250 ohm 10 watt resistors, okay? And they're just in line with the plug. So we got the end of our winding here on our primary is out to the plug. Same thing from this end to the plug. So if I go across the plug, okay, we should get a value that's very close to 660 ohms. As a matter of fact, you can see it right there. If I can get a good enough connection there, it's 646. So yeah, a minor difference there, but a far ways closer than the 158 we got there without those resistors. So we're close. We're like, 20 something ohms off, less than 20. Go back to pins. Yeah, 646, so 14 ohms off. That's about it. So there's not going to be a whole lot of DC resistance mismatch there, a little bit, but we are now closer to what we expect to be coming from our diagram, which I feel is one of the most appropriate first steps. So concerning DC resistance on our primary, okay, we needed 660 ohms. We put in some 10 watt resistors at 250 ohms each, and our total value was 646 ohms. Okay. So, like I said, trying to get our numbers as close as possible. And why 10 watt resistors? Well, our power calculation gave us 8.5 watts. So we have some overhead there. They're not going to get incredibly hot unless if they were underrated in power. They're about 1.5 watts overhead. What I expect to see as far as power consumption at the speaker, which I think is relatively safe. Okay, now the next thing that I wanted to consider is our AC impedance. Okay, so for AC impedance, we need to look at our plate-to-plate voltage of our F6G vacuum tubes. Hold on a second. More specifically, what I need to look at is, where is it at on this? Here we go. Here we go, right here. Push-pull class A, we're looking at our effective load resistance plate to plate, and we get 10,000 ohms. So that's 10,000 ohms of impedance. Okay, there goes the third consideration. 10,000 in the weird little W thingy ohms impedance, AC impedance. Okay, this was DC resistance. This one is AC impedance in our consideration, and that is the impedance between the primary and secondary winding, respective of what's required by our push-pull amplifiers. Okay, now there's a test that I'm going to do for this, albeit, and I should have mentioned this in the other video, especially when I was playing with that power transformer. Look, the things I'm doing in my office are dangerous. I don't touch that stuff when there's anybody else around. I make sure that I don't have any wires crossed or shorted. And then secondly, I don't do these measurements or any of this testing unless I'm on an isolation transformer, a variac, and I'm hooked into my dim bulb tester, because that is my current limiter. That's the thing that I am depending on if I make a mistake of not getting excessively electrocuted. Okay, that's my safety device. So if you do any of these things, you're doing so at your own risk. And I feel like I need to state that, especially given a lot of people come to YouTube to watch videos and learn how to do something, but they don't understand all the inherent risks. Okay, so if you have any hesitation towards any of the things that I show in this video, it'd probably be best that you just simply don't do it. That being said, let's get over into how I will calculate the impedance and which output to use from this audio transformer. Okay, some things I'm going to do is I've got my isolation transformer, variac set up, current limiter on, and then, I realize this is janky. This is why I say don't necessarily copy me. I need to do something else in the future to get rid of this janky nonsense. But I've got my my AC voltage set to 10 volts AC, okay? And then I have it going to the input of either side of the winding on our primary here. Now, I'm going to find a nice place to put this, my phone, while I'm recording this, so that way you can see the measurements I'm making, because we need to determine our turn ratio. So we need our input voltage and we need an output voltage, and we've got some calculations to do after that. Okay, hopefully this is recording well enough and you can hear me. All right, let's first measure our voltage on our primary. And hopefully my phone doesn't fall over here. But I'll set this up right here, and hopefully you can see that there in the bottom left-hand corner. But again, going right off our input here, you're getting, come on now, 10 point, my finger will stop slipping, 10.06 volts AC, or 10.07. I mean, it's practically there. We'll just call it 10 volts, okay? So no matter what, our input's going to stay at 10 volt. And so I'm writing down input 10 volt, okay? Now I need to measure my output windings, all right? The secondary, and we're going to measure it, I'm just going to do 3 examples here, okay? We'll do it from, because this has multiple taps on it, we'll do it from taps, let's see, 5 and 6. We'll do tap 4 and 5. And we'll do tap 3 and 4. I think that will give us a nice range of data. So I've recorded that down at the output. Okay, 5 and 6, 4 and 5, and 3 and 4. And we'll take a voltage measurement at each one and then record that down as well. So at 5 and 6, I am getting 0.135 volts AC. That was 0.135 volts AC. So 4 and 5, I am getting 4 and 5, 0.126 volts AC. So 0.126 volts AC. And then 3 and 4, what are we getting there? 3 and 4, we're getting 0.099 volts AC. Hopefully that was in recording view. 0.099 volts AC. 0.099 volts AC. Okay, that's essentially all I need from this, so I can power it down. We'll go back over to the bench. All right, now it's time to do a bit of math. For us to do here. Okay, so 10 volt input. Now we take 10 and divide it by 0.135. 10 divided by 0.135. We have a ratio of 74 turns. We'll include that 0.07 to 1 essentially. So that's going to be 5 and 6. Okay. For 4 and 5, we're looking at 10 divided by 0.126. So our ratio is going to be 79.37. We'll call that. Stop the digits right there and just round up. And then 10 divided by 0.099. And that gives us, for 3 and 4, 101. And we'll just round it up there. I mean, we could do the 0.01, but it's just for repeating, really. Okay, so in order to get our impedance, and remember, we're looking for 10,000 ohms of impedance here. What we then do is we square our ratio. So 74.07 times 74.07. Our impedance for pins 5 through 6 is 5,486. So pretty substantially low. Let's see, 79.37 times 79.37. There we go. 6,000. We'll just call it an even 300. Again, a lot lower than what we're looking for here. And then 101 times 101. That gives us an impedance of 10,201. So it's beginning to look like this is going to be our better option. Okay. Now, when we look up the actual part number for the old transformer, we could see that the 32-7754 paired with a 6F6G pentodes push-pull amplifier. We were looking at the output primary 660, field coil 660. Our voice coil impedance, meaning these two right here, we expect 1.25 DC ohms or 1.25 impedance. Okay, sorry, not DC resistance. All right, so we've got one further calculation to do. Okay, so what I'm going to do is, we know that our uh, what we're looking for our speaker impedance is 10,000 ohms. We can take, or another nomenclature you use for this impedance here is WR2, but we're just doing that. If I take, say, 10,000 and divide by ohms, okay, let's look at this. All right, 10,000 divided by 5486 would need a 1.8 ohm speaker, and our speaker impedance, sorry, little ohm, but speaker impedance was 1.5. Okay, another target. Let's see, that's 1.8. Oh, we got a storm coming in. Let's do 10,000 ohms divided by 6,300. It's too much. That's 1.5. And then we'll do the last, or 1.6 actually. And then the last one, we're going to do it divided by 10 to a 1. And we get kind of a sub ohm 0.98, where we just call it a 1 ohm speaker. Okay. So when I look at this, I'm trying to match up everything as close as possible. We're fairly close on our DC resistance. Okay, 646 versus 660. If I'm looking at the impedance of my voice coil, 1.5, 1.5 when we go from pins 4 and 5, but our impedance ratio is significantly less than here. Okay. However, if I go from our impedance ratio, I mean, we're slightly mismatched impedance here, but not as far out as with pins 4 and 5, although our voice coil, we're looking for 1 ohm of impedance here versus the 1.5 that we know we have from the tech data. So what I'm going to go with actually, with all these given numbers, is I'm going to go with pins 3 and 4, okay? Because that is the closest I can get between essentially our power, our DC resistance, and our AC impedance, respective of the output transformer and our voice coil. And so I'm going to wire it up from there, and we'll plug it into the radio. Now, I don't get as good a reception in my office as I do in other areas of the house, mainly too many LEDs and switch mode power supplies, but that's a shortwave station I was able to pick up somewhere around 10 megahertz or so, but or prior to 10 megahertz, but anyways, yeah, pretty good range of volume. So this is where I'll leave it. Well, ladies and gents, that's pretty much how I made those determinations, and the math involved and everything for the audio output transformer. Again, any vintage radio guys or gals who watch this video, if you have a preferred method, or if you can point out any mistakes that I've made, and you can present a better way of doing this in a logical fashion, then feel free to please leave comments in the comment section or email me, and be happy to learn a little bit more from those groups. But that being said, I felt like I wanted to come back and demonstrate what went into that, since I didn't include it in that video, and obviously watch that video to see the final alignment and hear the radio operate after everything was all said and done. Anyways, take care and goodbye.
Bart?